Greetings, welcome to Brain Gauge channel. This little talk is on the brain gauge metric plasticity. Plasticity is a fairly important measure because as many people watching this know, plasticity is something that basically relates to how well your brain adapts to the environment. And plasticity does happen on many different scales. Happens on millisecond, second, minute, hours, weeks, months, years. There's a lot of different time scales that it is involved in. And not only that, you can measure plasticity in a number of different ways. And reflecting that is that we actually have different ways to measure it. And, it's that it can be derived from a number of different measures, but it is a computed measure. And which measures it's computed from has to do with which measures are in your test battery. And, a lot of people don't realize this, but different people use different test batteries. And it really depends on how much time do you want to spend testing and or what is your specific application. But anyway, in this particular talk, we're going to talk about the plasticity metric that's derived from simultaneous amplitude discrimination and single site adaptation. This is a single site adaptation metric. That is one of the first that we developed, and it's very well published. So anyway, let's just go through exactly, what do we mean by adaptation and single site adaptation in particular. But first, let's talk a little bit about the concept of illusory stimuli. Now, basically, what we want to do is deliver illusions or make perception change. And, if you look on the left, you see, a question of how many triangles are drawn. The answer is none. And actually, the triangles you see are a result of the brain connecting the dots. That's a simple answer. On the right, if the question is which center circle is larger, what you have is a context-dependent illusion. And while this center circle seems a little smaller than this center circle, you can say they're actually identical in size. It's just that one looks bigger than the other because of the context of what's surrounded by. And we can do something very similar with the brain gauge test, and that's actually what we do. So let's see how we do it. Well, remember the amplitude discrimination test. That would be this test right here, where the question is which of these two is larger. So how could we change the percept so that would be different, or to create an illusory condition? Well, the easiest one would be like with a context-dependent illusion, where we deliver a stimulus to this finger and no stimulus to that finger. And then this stimulus now, which is right after this stimulus is delivered, is going to feel smaller. So we've delivered one conditioning stimulus to one finger, and now we deliver another stimulus to that finger, but it's going to feel smaller because basically, your brain just gets bored. You adapt to this stimuli, responsivity goes down, and overall mean firing rate goes down, and you feel bored. You're basically not interested. But this stimulus gets smaller, so it's going to be harder to tell. So let's look at the results, some typical results from that kind of trial or test. Well, let's look at first just plain old amplitude discrimination is this black line here. And it's also on the red and the black line. You track down, and you're tracking down to threshold. So this threshold tracks down to about 10 or 15%. And, smaller numbers are better for amplitude discrimination. But now if you add this illusory conditioning, you get something like this. In other words, the tracking does not go as well. And this person does not track down like they did for over here. All right, now if you add up everybody that's done this for this particular condition, you get, amplitude discrimination in the 25 micron range, which is again normal. That's basically what that is. And when you add the illusory conditioning stimulus, it goes up to about 70, 65 or 70. So this difference here is actually the conditioning or the adaptation metric is the difference is due to that single site adaptation or that single site conditioning stimulus. So see this big difference right here? That's good, okay? Because if generally when you have some neurological insult, you don't see a difference between amplitude discrimination and the single site adaptation metric. So let's take another look. Let's, just being a nerd, I'll show you the science that some of the science that back this up. Again, this is tracking for amplitude discrimination. If we continue tracking, this is with a lot of subjects and the average of a lot of subjects, continue tracking, doing the amplitude discrimination test without any single site adaptation, the values for control are pretty solid. Now let's do a 200 millisecond single site adaptation. That's about the same size as that larger stimulus. And it goes up a little bit. Then 500 milliseconds goes up some more. 1 second, some more. 2 seconds, some more. So this is one of the parameters for single site adaptation is looking at these different values. And so longer, it's fairly linear, it's a fairly monotonic thing. Increase the stimulus duration of the illusory confound, and that goes up. And you can see that over here. Single site adaptation, all these values go up in a pretty systemic way. This DSA over here, what you see is here block 1, here's control, amplitude discrimination. All of a sudden you get better, smaller numbers are better. That's because we stimulated both sites. You stimulate both fingers in the dual site adaptation condition. Not many people use this particular thing, but you do get better with dual site adaptation. But the signal and noise ratio is better with single site adaptation. That's why we do the single site adaptation. You just see bigger numbers, bigger changes is what we're looking for. So anyway, what you want to look for is a big change, after this. And if you looked at the difference between amplitude discrimination and single site adaptation across all these different ages, it's fairly constant, and that's good. So that big difference is really what you're looking for. It remains constant as long as you have healthy aging. And we talk a little bit about this in the aging and plasticity talk. But, that's really what you're looking for. Now, when does it change? When does this plasticity metric or this difference between these things go down? Now, if we just measure the difference, and we just call that the adaptation metric, controls have a difference, basically the difference between single site adaptation and amplitude discrimination. It's about this high. And then for all these different neurological disorders, those values go way down. Now, that's fairly, the reason it's so agnostic or so non-specific for this plasticity measure is because so many different mechanisms go into that. And so it can be, it can be excitatory or inhibitory. The brain's made up of excitation and inhibition, and, you can have problems with both. One or the other or both. Either way, it will impact plasticity. Let's just look at, all these different conditions. The red is where you have some kind of impaired or neurological insult. Green is recovery from those insults or some kind of treatment. 2 examples though. Migraine. Don't see much recovery with treatment. That's because the treatment in this case for migraine was pharmacological, and giving opioids to people does not improve their plasticity, just makes them feel better. All right, and over here, we have centrally mediated pain getting better, but over here, peripherally mediated pain is basically, it's already fine. Plasticity is fine with acute pain. It's long-term pain that's or chronic pain that you don't get recovery, that you're getting recovery from. You see this very low adaptation metric for chronic pain, but for something that's peripherally mediated, it's an acute version of pain, plasticity still hadn't been impacted. All right. Anyway, let's take one more look, just for fun, look at some of the science behind this. Again, here's your graph, and you're saying, what does this mean? Think of single site adaptation as a way to see what the effect of turning down responsivity is. If you deliver a stimulus to the skin for a long time, or deliver any stimulus, the same stimulus over and over and over, which is essentially what single site adaptation is responding to, and measure the response, higher numbers of response, and these are spikes per second, has to do with mean firing rate of neurons in the brain, you see this trend down. Okay, so you keep firing and giving the same stimulus over and over and over, these neurons go down and become less responsive. However, think about it this way: the brain is getting bored. You give it the same stimulus over and over and over, it gets more and more bored. But what does it do? Why does delivering stimuli to two fingers actually improve performance? Shouldn't it get bored? Well, responsivity goes down, but you actually improve performance. And the reason you improve performance is because you improve contrast. Responsivity overall goes down, efficiency goes up, because look at this, initially you get an early response, but as you do more and more stimuli, you get a more interesting response and patterns get carved out. And that's really the whole point of the thing, what you want to measure. You want to, those changes in responsivity also parallel the contrast enhancement. And, what we want to do is measure that and see, and that's a very important feature of plasticity. Anyway, if you have any questions about plasticity, please send them my way. Always happy to talk about it, and hope that made some kind of sense. Have a great day.